All right, we're into part two, or page two, the back of page one. I don't know how you want to say it, but however you want to say it. Sodium and potassium are soft metals that react violently with water. Predict two other elements on the periodic table that would have the same traits. Well, what I just said was things that have the same number of valence electrons, and I told you that these things blow up in water. So they said sodium and potassium, that's Na and K. Well, guess what? Rubidium, cesium, and lithium. So rubidium, cesium, and lithium all do the same thing. And why I chose those elements? Same number of valence electrons. That's what makes things react the same in the same group, right? I could have said in the same group too. That would have been, but the reason why it's not just because they line up in a line together. It's because they have the same number of valence electrons. Fluorine is often added to toothpaste to help kill germs. Iodine is used in hospitals to prep patients' skin for surgery. Identify the group to which each element below belongs. Which element below might you be able to use for killing germs? Well, they use fluorine and iodine, and bromine is in the same family, so I'm going to say that I can use bromine, which is part of the halogens. And I'm going to circle bromine just so I can say that that's the element that I might be able to use. Boron is in the boron family. Barium is in alkali earth metals. Alkali earth metals, there's barium. Element K is bigger than element J. Where is element K located on the periodic table? To the left or below? Below J. Because remember, our trend for atomic radii is down and to the left. That means any two elements, the one to the left is bigger. Any two elements that are in the same group, the one on the bottom is bigger because we add more shells, right? The reason things are bigger on the left is because they have less protons and the same number of shells, right? Which are the most stable elements on the periodic table? Noble gases. Yeah, by now you should know that. And again, they use that stable elements. You have discovered several different mystery elements. Based on the chart below, identify the elements as copper, silicon, or sulfur. Okay, well, what you got to know is that copper is a metal, silicon's a metalloid, and sulfur is a nonmetal. So basically, I'm looking at the properties of and deciding which ones are properties of metals. Well, shiny and malleable, conduct electricity, react with acid are all metal properties. So copper, the metal, is going to go there. Dull and brittle, not conductive, does not react with acid. That's the exact opposite of a metal, so that would be non, so that would be sulfur. And if I'm correct, then this last one should have both brittle and lustrous. Semiconductive, does not react with most acids. That's got to be silicon, right? Yeah, because that's a metalloid, a non-metal, and a metal. And metals are shiny and malleable, conduct electricity, and react with acid. Non-metals are dull and brittle, not conductive, do not react with acid. And metalloids can do a little bit of each. So this is brittle but shiny. It's semiconductive, but it does not react with most acids. All right, identify the following elements. I have 4 valence electrons. Okay, so we're going to go to group 4A, and then it says I'm in the 3rd energy level, so I am silicon. Silicon is in the 3rd energy level. It means it has 3 shells, 3 energy levels. It's in the 4th group. That means it has 4 valence electrons, and so therefore this element is silicon. I have 2 valence electrons and I'm in the 4th energy level. Well, 2A has 2 valence electrons, and I'm in the 4th energy level, right? Did it say 4th? Yep. Yep, 4th energy level, 2 valence electrons, so I am calcium. So what we're trying to get you to do here is start identifying where these things are, what this periodic table means, what all these numbers mean. Oxidation numbers, what tends to happen with electrons because of the number of valence electrons. Number of valence electrons predicts our properties for reactivity. Okay, define atomic radius. It is 1/2 the diameter. I could give a real basic, but I'm going to say it's the size of the atom, right? On the diagram below, describe the periodic trends. Well, I'm going to describe one trend. Now, you have to know that things get bigger as we go down and to the left. So these are the 2 arrows they're actually asking. Moving across a period and down a group. Why? More shells. More shells as I go down. Less protons as I go from right to left. So I have that outstanding picture. Where's that picture? There it is. This picture here. So the reason they get bigger as we go down, because this has 2 shells, this has 3, this has 4. That means it's in the 2nd, 3rd, and 4th energy level. You see why they get bigger. Why do we get bigger as we go from right to left? Well, because we have less protons. It's called less nuclear charge. So for the same number of shells, this has 3 protons, which are the magnetic opposite of electrons, right? They're trying to pull these electron shells in tight, but there's only 3 of them. Over here, it's like having 9 guys pulling these shells in, and they can pull them in very tight. So really, your answers are more or less shells, more or less protons for everything on the periodic table. That's why the trends are there. That's why they exist. So, more shells, that's why I get bigger as I go down. Less protons, that's why I get bigger as I go from right to left. Okay? All right, we're going to start page 3 of this thing. Place the following in order from largest to smallest. All right, so we have boron, beryllium, and lithium. So we have this, this, and this. And they want to go from largest to smallest. So largest is going to be lithium, right? And then it's going to be beryllium. And then it's going to be boron. And you got to make sure you pay real good attention, largest to smallest, smallest to largest, because both answers will be on any test you're given. You know, they love to give you those good wrong answers, but so be careful with that. When it says largest to smallest, make sure you know what largest to smallest means, or increasing or whatever. Okay, from smallest to largest, see right here, they have the exact opposite, and we've got bromine, chlorine, and fluorine. So fluorine is the smallest, so we're going from smallest to largest, because fluorine is the higher up this way. Chlorine, bromine, and we know that you're just adding shells as we go down. Yeah, because I'm adding shells, more shells. Why did I place lithium, beryllium, and boron in this order? Because increasing number of protons. That's what I really should have said here, is increasing number of shells. Increasing number of shells, right? So that's why things get bigger, is because of an increasing number of shells. I have 2 shells, 3 shells, 4 shells. And here they're getting smaller because I have more protons, an increasing number of protons. Boron has 5, 4, 3. And it makes a difference on the size of the atom. All right, place the following in order from largest to smallest. Cobalt, nitrogen, rubidium. All right, nitrogen is here, cobalt is here, rubidium is here. So you have different reasons, but that's where the trend points. So it's very easy to decide which one's smallest, which one's biggest. They want them from biggest to smallest. So rubidium, cobalt, nitrogen, right? Rubidium, cobalt, nitrogen. So rubidium, cobalt, nitrogen. Why did I place them in this order? For a variety of reasons. Rubidium, because it has more shells. Um, I mean, it just straight up has more shells than cobalt. It has one more shell than cobalt. And nitrogen, because it has less shells and and an increased number of protons for those number of shells. So as long as you know the trends, you'll be able to answer these questions pretty easy. Define ionization energy. Well, that is the amount of energy needed to remove one electron. N electron. Energy is in the word, ionization energy. So whatever your answer is, it should have the word energy in it. And it is the amount of energy needed to remove an electron from an atom. So I want you to think about what I'm doing. I've got protons in the center, and here I'm going to have helium. So what I'm trying to do is grab this electron and pull it off of here. And it takes a certain amount of energy to do that. Based on nuclear charge, based on how many shells get in the way. So let's talk about it. Let's first draw the trend. So the trend for ionization energy is up and to the right. And it includes everything, including noble gases, because you can remove an electron from a noble gas. And it says explain why these trends occur. Okay, so the uptrend is because less shells shielding, right? So you got to think. I'm trying to remove an electron from this. This is helium. It's all the way at the top. It's right here, right? Look at the proximity of that nucleus, which is trying to hold that electron. They are right beside each other. Now let's talk about, we'll talk about xenon, which has 5 shells. Now I'm going to put my charge here, and then I'm going to start drawing my shells. And already I can see that I'm going to have a problem because I've got 4 shells and I'm already into my question. Now think about this electron out here. And think about the distance between these two. And it's a lot easier to pull this electron off. So things on the bottom have less ionization energy. They require less ionization energy because of less shells. Okay? Now, let's talk about across the periodic table. Why is it harder to get an electron off of fluorine than lithium? Well, fluorine has more nuclear charge. It has more protons than lithium for the same number of shells, so the distance is closer. I want you to think about an electron here, and a positively charged nucleus for each of these. This is right beside it. It's really hard to pull this off. This requires a lot of energy, and it has 9 protons holding it on there. This has 3 protons holding this electron on here. So it's not trying very hard to hold it on there. Increased nuclear charge. Or to put it very simply, more protons. Stuff on this side has more protons for the same number of shells. 2 shells, lithium has 2 shells, fluorine has 2 shells. 3 protons, 9 protons. All right, so I'm going to begin video 3 here momentarily.